Hi everyone, back in a new awesome video, and today we're going to continue with our series about electricity and magnetism. Today we will continue treating the topic of electric potential. Specifically, we will calculate the electric potential difference between two plates, two spherical cells, and two cylindrical cells. So, let's start. Right, now let's try and find the electric potential difference between two plates. If you recall from our previous videos, we found out that in Gauss law, the applications of Gauss law, we found that these two plates generate a constant electric field between them, and the magnitude of that electric field is this one, minus sigma, that is the superficial charge density, over epsilon naught in the minus j direction, because it goes from the positively charged to the negatively charged. Now we're going to choose a path in which we're going to integrate to find the electric potential. We could choose any path in each of these directions, but that will complicate things unnecessarily, and it doesn't matter because the only change in potential and in electric potential we're going to find is along the electric field lines. So this direction is going to make sure that we just get all of it without adding any unnecessary terms. If you recall from last time, the change in potential energy equals minus from A to B of the electric field times ds. In this situation, ds is going to be dy in the j hat direction, and we're going from minus d2 to d over 2. So we will have this to be minus from minus d2 to d over 2 of this, which is going to be minus sigma over epsilon naught in the j hat direction times j hat dy. So we have some cancellations to make over here. The j hat with the j hat give 1, and the minus with the minus gives us a plus sign. We see that this is a constant term under the change of y, so we can just take that out of the integral, and we are left with sigma over epsilon naught, and we're going to have a d over 2 plus a d over 2, which minus d over 2, it's plus, and we're left with sigma d over epsilon naught. So what we see over here is that the change in electric potential, it's equal to sigma d over epsilon naught. And what we see really is that by going from here to here, the electric potential has raised. Therefore, this is at a lower potential. We can also see that these electric field lines go perpendicular to the change in potential, that is, to the equipotentials, because we would have a line of same potential around there, a line of same potential around here, and the plates itself are some lines of equipotential. So, and we see also that it is going from the higher potential to the lower potential. That way, we get an understanding that a positively charged particle that follows these electric field lines is always going to go flowing down the potential flow. In a sense, you can think of this as kind of a mountain and this to be a valley, and then the electric charge, the positive electric charge, goes this way. However, negatively charged particles go against the electric field lines and will go from lower to higher potential. Alright, now let's explore what happens when we have two spherical cells. If you recall once again from our applications of Gauss laws videos, we found that this system is divided into three regions. a small region on the inside of the first spherical cell in which there is no charge inside of it, and therefore it has no electric field. So E equals 0 in this region. Also, we have the outside part in which both parts cancel and the electric field is also equal to 0. And now we have this part in which there is effectively an electric field going in this direction, well, in all directions, and it acts as if this small charge was a point charge. Therefore, our electric field on the region, well, that's not an E. An electric field on the region 2, we'll call it, is going to be BQ over R squared in the R hat direction. Now, we already know that the electric potential for a point particle, which is exactly the same in this case, is equal to KQ over R. We're going to calculate the electric potential difference from going from this point A to point right over here B. And just in case that's not clear, that's an A. So to calculate this, we have the electric potential at both points because we can use our formula. Therefore, what we find is that the change in potential equals the potential at B minus the potential at A, which is KQ, the distance in this case is B, minus KQ, and the distance in that case is A. So we can take the common factor out, and we have 1 over B minus 1 over A. And we could calculate that and get that the change in potential is going to be equal to KQ of A minus B over AB. And that is the difference in potential between two spherical cells. Wait, now we are just missing the case of two cylindric cells to exploit all the different symmetries we also used on our applications of Gauss law videos. We already found in those videos this simple expression for the electric field inside these two spherical cells between them, because in this region, once again, it's going to be 0, and the outside region, once again, is going to be 0. In this case, to find the electric field, we're going to use the definition, the electric potential, sorry, once again, messing now. We're going to go from A, right around here, to B, right on there in this direction, and then the change in potential energy delta B is going to be equal to minus A to B of the electric field R times ds. Now in this case ds is going to be equal to a dr because this is in the r hat direction. So what we're going to get is some limits that are also going to be r's, values of r, which are going to be a and b, a small a and a small b. So from a to b of this quantity, note this first part is a constant. Now we'll have an r hat times this, which is going to give us a dr, and we're missing a 1 over r. We're going to write it right around here. You realize that is a constant, so no problem with that. And then we're going to have a 1 over r over here, which its integral is going to be the logarithm, the natural logarithm. Therefore, we're going to get a minus lambda 2 pi epsilon naught logarithm of r from a to b. And what we find is this is going to be by the properties of logarithms minus lambda 2 pi epsilon naught log of b over a. And what we're going to do now is to get this negative sign into this quantity. And if you realize this now is a positive quantity because B is bigger than A. Therefore, we will leave it in this form because it's more apparent that the change is going to be a negative change. And that makes sense because we are going from the higher potential plate, which is this one inside, to a lower potential cylindrical cell, not plate, cylindricals. So it makes sense that this change is negative as we are going from positive to negative and in the same direction as the electric field lines. That is all for today. I hope that these examples help you gain a more thorough understanding of how electric potential energy, electric field, and all these different quantities we've been introducing are all related. Because in the end, since we started with Gauss' law, everything has led us to this moment in which we are able to apply energy principles to electricity. And that is a very important step because, as you saw in our classical mechanics series, energy principles are very powerful. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!